The celestial formation known as the Smiling Galaxy Cluster, formerly designated SOSS J1038+4849, stands as one of the most remarkable examples of gravitational lensing in the observable universe. Captured in exquisite detail by the Hubble Space Telescope, this cosmic structure is not merely a visual delight but also a profound source of scientific intrigue. Its smile, formed by arcs of light, is an optical illusion created by the gravitational warping of light from distant galaxies behind the cluster. This phenomenon offers researchers invaluable insights into the enigmatic distribution of dark matter, the underlying structure of the universe, and the interplay of massive galactic clusters. At the heart of the celestial smirk, a dense collection of galaxies acts as the gravitational lens, bending the light from even more distant galaxies into arcs. This effect is a direct consequence of Einstein's theory of general relativity, which posits that massive objects distort spacetime, influencing the path of light traveling through it. The arcs forming the eyes and smile of this cosmic face are the stretched and magnified images of background galaxies, giving astronomers a rare opportunity to study these remote stellar systems in greater detail than would otherwise be possible. In addition to its aesthetic appeal, SOSS J1038+4849 plays a critical role in advancing our understanding of dark matter. Since dark matter does not emit, absorb, or reflect light, its presence can only be inferred through gravitational effects. The distribution of dark matter within the cluster can be mapped by analyzing the precise distortions in the arcs and rings caused by gravitational lensing. By studying these distortions, scientists can construct mass models of the galaxy cluster, revealing not only the location of dark matter but also its relative density and influence on surrounding structures. Further studies of this galactic grin have utilized multi-wavelength observations, combining optical, infrared, and X-ray data to paint a comprehensive picture of the cluster's composition and activity. X-ray emissions detected in the region indicate the presence of superheated gas trapped within the cluster's gravitational potential well. This gas, reaching millions of degrees in temperature, is a vital component of the cluster's total mass and contributes significantly to its gravitational lensing power. The luminous lens has also become a focal point in research exploring the formation and evolution of galaxies in the early universe. The magnification provided by gravitational lensing allows astronomers to observe galaxies that formed mere hundreds of millions of years after the Big Bang. These young galaxies are often too faint to be studied directly, but the lensing effect amplifies their light, enabling detailed spectroscopic analysis. Through these observations, scientists are piecing together the processes that govern star formation, galaxy mergers, and the growth of supermassive black holes in the universe's infancy. Moreover, the study of gravitational lenses like the cosmic arch aids in refining cosmological models. By analyzing the distortions in light caused by such lenses across vast cosmic distances, researchers can measure the Hubble constant, a critical parameter that quantifies the rate of expansion of the universe. Discrepancies in measurements of the Hubble constant obtained through different methods remain one of the most perplexing challenges in modern cosmology, and systems like SOSS J1038+4849 are crucial in addressing this tension. The discovery and continued exploration of this galactic smile exemplify the synergy between advanced observational technologies and theoretical physics. While its iconic appearance has captured the imagination of the public, its true value lies in the wealth of scientific data it provides. Each arc of light represents an untold story from the cosmos, a story of galaxies billions of light-years away, of dark matter shaping the universe, and of the fundamental forces that govern existence. SOSS J1038+4849 is not merely a happy accident of the cosmos, it is a testament to the interconnectedness of all things, from the smallest particles to the grandest galactic structures. As telescopes grow more powerful and computational models more sophisticated, this celestial wonder will undoubtedly continue to yield new discoveries, deepening our understanding of the universe and our place within it. Beyond the current studies, the Smiling Galaxy Cluster offers vast potential for future research, especially as next-generation observatories like the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory come online. These advanced facilities will allow astronomers to probe even deeper into the cluster's structure and the distant galaxies magnified by its gravitational lensing. The JWST, with its unparalleled infrared sensitivity, is particularly well suited for studying the faint, redshifted light of the most distant galaxies amplified by this lensing effect. Observations through SOSS J1038+4849 are expected to reveal the chemical composition, star formation rates, and structural evolution of these primordial galaxies, helping to refine models of how the first galaxies formed and evolved. Additionally, the JWST can detect the presence of early supermassive black holes, shedding light on the mysterious processes that allowed such massive objects to form in the early universe. The Vera C. Rubin Observatory, on the other hand, will provide a complementary view through its wide-field imaging capabilities. By capturing transient events within the cluster, such as supernovae in lensed background galaxies, the observatory will allow astronomers to measure time delays between multiple images of the same event. This phenomenon, known as time delay cosmography, offers a unique method for measuring the Hubble constant with unprecedented precision. These measurements will be critical for addressing the ongoing Hubble tension, a major unresolved discrepancy in cosmology. Meanwhile, simulations of the cosmic grin using advanced computational models are becoming increasingly detailed. These simulations not only recreate the lensing effects observed in SOSS J1038+4849 but also incorporate theoretical predictions about dark matter's behavior and distribution. By comparing simulations to actual observations, scientists can test the validity of different dark matter theories, including whether dark matter consists of weakly interacting massive particles, WIMPs, axions, or other exotic particles. SOSS J1038+4849 also serves as a natural laboratory for understanding galaxy cluster dynamics. The galaxies within the cluster are not stationary, they move under the influence of the cluster's gravitational field and interact with one another. These interactions can trigger star formation, disrupt galactic structures, and even lead to the merging of galaxies. By studying these processes in detail, researchers can better understand the role of environment in shaping the evolution of galaxies. Another promising avenue of research involves the cluster's impact on the cosmic microwave background, CMB. As the relic radiation from the Big Bang passes through the galaxy cluster, it is subtly distorted in a phenomenon known as the Sunyaev-Zeldovich (SZ) effect. This effect provides a powerful tool for measuring the cluster's total mass and temperature, as well as for probing the properties of dark energy, which drives the accelerated expansion of the universe. One of the most intriguing possibilities involves searching for evidence of modified gravity theories. Some alternative theories of gravity, which aim to explain cosmic acceleration without invoking dark energy, predict subtle deviations in gravitational lensing patterns. The high-precision data from systems like SOSS J1038+4849 could reveal these deviations, offering a direct test of such theories and potentially revolutionizing our understanding of gravity itself. The smiling face in the cosmos is also a poignant reminder of humanity's growing ability to unravel the universe's deepest mysteries. Its discovery and study represent decades of technological progress, theoretical innovation, and international collaboration. While its cheerful appearance has drawn widespread public attention, its true significance lies in the countless scientific opportunities it provides. In a way, SOSS J1038+4849 encapsulates the dual nature of astronomy. It is both a source of profound scientific inquiry and a source of wonder that connects us emotionally to the cosmos. As humanity continues to gaze deeper into the universe, clusters like this one will remain beacons of curiosity and discovery, guiding us toward new horizons of understanding. Yet, what truly sets the cosmic smile apart is its ability to pose more questions than answers, questions that challenge the limits of human understanding. What lies beyond the lensed galaxies that we can see? Are there even more ancient structures, obscured by the dense veil of spacetime distortions, waiting to be uncovered by future advancements in observational technology? Each faint arc of light represents not only the history of a galaxy billions of light-years away but also a portal into a time when the universe was still young and chaotic, shaped by forces we are only beginning to grasp. One of the most tantalizing mysteries hidden within SOSS J1038+4849 is the nature of dark matter itself. The gravitational lensing patterns we observe cannot be explained by the visible matter in the cluster alone. There must be an invisible mass component exerting an immense gravitational pull. Could this invisible architect of the universe be composed of particles we have yet to discover? Or, more intriguingly, could it point to an entirely new framework for understanding gravity and spacetime? Moreover, the eerie precision of the smile itself sparks curiosity. Although the arcs and features can be scientifically explained by gravitational lensing, their almost anthropomorphic arrangement feels uncanny. It serves as a cosmic Rorschach test, igniting debates about our innate human tendency to find patterns, even in the chaos of the universe. This formation invites us to wonder, what other stunning visual phenomena might exist elsewhere in the vast expanse of space, waiting to be stumbled upon? Some researchers speculate that the regions magnified by this cluster might hold clues to one of the most elusive phenomena in modern physics, the cosmic web. The cosmic web is the intricate network of filaments and voids formed by dark matter and galaxies that spans the entire universe. Observing these lensed galaxies at different redshifts could help map this structure in unprecedented detail, potentially revealing how galaxies are funneled along these filaments to form clusters like the smiling galaxy. The cosmic grin also beckons the question of whether such phenomena could play a role in the search for extraterrestrial intelligence. If advanced civilizations existed in these distant galaxies, might they also be studying the lensing effect caused by their own galaxy clusters? Could gravitational lensing itself become a form of cosmic communication, amplifying signals across unimaginable distances? While speculative, these questions highlight the interconnectedness of every discovery in astronomy and its potential implications for understanding our place in the cosmos. Even more fascinating is the possibility that the light magnified through SOSS J1038+4849 contains signatures of the first stars, so-called population 3 stars. These stars, theorized to be the universe's first light sources, were composed entirely of hydrogen and helium, burning at incomprehensible temperatures and living short, explosive lives. Detecting the chemical imprints of these ancient stars would rewrite the story of the early universe, offering a direct glimpse into the very origins of light and matter. As we continue to study this smiling anomaly, one truth becomes increasingly clear: the more we learn, the more the universe reveals its boundless complexity. What began as a charming cosmic coincidence, a face staring back at us from the stars, has grown into a profound symbol of the mysteries that lie hidden in the fabric of spacetime. It's a reminder that every corner of the universe, no matter how distant or faint, holds the potential to reshape everything we think we know. In the coming decades, as humanity builds even more powerful telescopes, both on Earth and in space, the study of SOSS J1038+4849 will undoubtedly evolve. It is likely that this smiling cluster will not only continue to serve as a lens through which we peer into the universe's past but also become a touchstone for exploring fundamental questions about its future. Will the universe continue expanding forever? What role will dark matter and dark energy play in its ultimate fate? Could there be other faces in the cosmos, quietly waiting to be discovered? The smiling galaxy cluster is more than a scientific curiosity or an aesthetic wonder. It is a challenge, a puzzle, and an invitation. It dares us to explore, to question, and to dream. And as we stand at the threshold of new discoveries, it whispers to us the most thrilling promise of all, that the universe, in all its complexity, still has secrets to share. The smiling galaxy cluster is also a profound testament to the sheer scale and interconnected nature of the universe. The light we see from the lensed galaxies within this cluster has traveled billions of years to reach us, crossing unimaginable distances through a universe that has expanded and evolved since the moment these photons began their journey. In this sense, observing SOSS J1038+4849 is akin to looking through a time machine, offering us a snapshot of the cosmos as it existed eons ago. But this glimpse into the past isn't static, it's dynamic. The light curves, distortions, and relative positions of the lensed galaxies change with time, albeit on timescales that challenge human perception. This has sparked interest in monitoring gravitational lenses like the cosmic smirk over decades to detect subtle changes in the background galaxies or even reveal new ones as the universe continues its inexorable expansion. This ongoing evolution offers an extraordinary opportunity to test and refine our cosmological models. One of the most intriguing areas of research involves the interaction between dark matter and visible matter in the cluster. Scientists have noted that the smile and other features of the lensing pattern align closely with simulations of dark matter halos surrounding galaxy clusters. These halos are thought to be the scaffolding upon which galaxies form and evolve. By studying how these halos distort the light of background galaxies, researchers can directly probe the properties of dark matter, its distribution, density, and behavior under extreme gravitational conditions. Some hypotheses even suggest that dark matter might interact weakly with itself, and gravitational lenses like SOSS J1038+4849 might hold the observational evidence needed to confirm or refute these theories. The gravitational lensing phenomenon also opens a door to explore regions of the universe that would otherwise remain forever hidden. Deep within the arcs and rings of light, astronomers are beginning to uncover faint galaxies that represent the building blocks of larger structures. These ancient galaxies are like fossils, providing evidence of the chaotic and violent processes that dominated the early universe. Their distorted images reveal how gravity sculpted the first galactic structures, merging smaller systems into the massive galaxy clusters we observe today. Interestingly, the smiling cluster is not alone in creating such mesmerizing effects. There are other gravitational lenses scattered across the universe, some forming equally breathtaking shapes, such as Einstein rings and cross-like patterns. What makes SOSS J1038+4849 unique, however, is the uncanny symmetry of its features, a near-perfect alignment that makes it one of the most iconic gravitational lenses ever discovered. This symmetry is incredibly rare and may provide clues about the cluster's specific geometry, mass distribution, and the line-of-sight alignment required to produce such a striking image. Another promising area of investigation is the role of gravitational lensing in magnifying transient cosmic events. Supernovae, gamma-ray bursts, and even kilonovae, cataclysmic explosions caused by neutron star mergers, can be magnified and distorted by galaxy clusters like SOSS J1038+4849. These magnified events provide a window into the most extreme environments in the universe, offering unparalleled detail about the physics of stellar deaths and the creation of heavy elements. For instance, the light from a supernova behind the cluster might appear multiple times, separated by months or even years, due to the different paths taken by light rays through the lens. By observing these repeated appearances, astronomers can measure cosmic distances with remarkable precision. Perhaps most exciting is the potential for gravitational lensing to aid in the detection of elusive phenomena like primordial black holes or exotic particles predicted by advanced theories of physics. If such objects exist, they could create subtle perturbations in the lensing patterns observed in clusters like SOSS J1038+4849. Detecting these anomalies would not only confirm the existence of these hypothetical entities but also open entirely new chapters in our understanding of the universe's fundamental building blocks. The galactic smile also serves as an inspiring symbol of the interdisciplinary nature of modern astronomy. Its study requires expertise in observational astrophysics, theoretical physics, computer modeling, and even artificial intelligence, which is increasingly being used to analyze the vast amounts of data generated by gravitational lensing studies. Machine learning algorithms can identify lensing patterns in telescope images far more efficiently than humans, accelerating the discovery of new lenses and enabling researchers to focus on interpreting the data. And yet, even as technology advances, the smiling cluster remains a deeply human story. It reminds us of the wonder and curiosity that drive exploration, the power of science to uncover hidden truths, and the profound interconnectedness of the universe. It challenges us to look beyond the surface, to see patterns where others might see chaos, and to find beauty and meaning in the most unexpected places. In many ways, the study of SOSS J1038+4849 is only beginning. As telescopes become more powerful and our theoretical models more refined, this smiling face in the cosmos will continue to inspire, challenge, and enlighten us. What other secrets does it hold? What new questions will it raise? Only time will tell. For now, the smiling galaxy cluster stands as both a puzzle and a promise, a beacon in the vast, uncharted sea of the universe, inviting us to explore further, dig deeper, and dream bigger than ever before. The intrigue surrounding the smiling galaxy cluster deepens as we consider the uncharted possibilities hidden within its arcs of light. What if the gravitational lensing we observe in SOSS J1038+4849 is just the beginning, a doorway to phenomena yet unknown? The universe has a way of surprising us, and this cluster may hold secrets far beyond what current scientific understanding can predict. For instance, scientists are beginning to explore the idea that gravitational lenses like the cosmic smile could reveal traces of exotic matter beyond dark matter, perhaps remnants of primordial black holes or even hypothetical particles like sterile neutrinos. These exotic entities, if present, could leave subtle fingerprints on the lensing effects, warping the arcs in ways that defy standard predictions. Could SOSS J1038+4849 be hiding such anomalies in plain sight, waiting for technology to catch up with its mysteries? Even more tantalizing is the idea that the light from this cluster might carry clues about the very fabric of spacetime. Some theories propose that the structure of spacetime itself is not smooth but rather has a quantum graininess at the smallest scales. This graininess, if real, could subtly distort the paths of photons traveling across vast cosmic distances. If detected in the lensing patterns of SOSS J1038+4849, it would revolutionize our understanding of the universe, potentially merging quantum mechanics and general relativity into a unified framework. But the mysteries do not end there. The background galaxies magnified by the cluster's gravitational field offer a window into some of the most extreme environments in the cosmos. Among these, astronomers suspect there may be evidence of early quasars, massive black holes devouring matter at the centers of young galaxies. These quasars, visible only thanks to the cluster's lensing power, could provide critical insights into the formation of supermassive black holes. Were these cosmic giants born massive, or did they grow over billions of years by consuming gas and merging with other black holes? The light amplified by the smiling cluster might hold the answers. And what of the strange symmetry of the cluster itself? While gravitational lensing is well understood in terms of physics, the precise arrangement of features in SOSS J1038+4849, a nearly perfect smile and eyes, remains a statistical anomaly. Could this symmetry point to an underlying order in the cosmos, something beyond random chance? Some theorists have even speculated that such alignments could be evidence of large-scale cosmic structures or patterns, echoes of the primordial conditions that shaped the universe in its earliest moments. Even more speculative are the philosophical implications of such discoveries. If the smiling cluster reveals a deeper cosmic order, what does that say about our place in the universe? Are we merely observers of an intricate, random ballet of matter and energy, or is there a deeper connection between the patterns we see and the nature of existence itself? This cosmic smile, while scientifically explainable, feels almost as if the universe itself is acknowledging our curiosity, encouraging us to continue asking questions. The study of SOSS J1038+4849 also challenges us to think on timescales far beyond human comprehension. The light from these distant galaxies began its journey when Earth was still forming, billions of years before life as we know it existed. This light has traveled uninterrupted through the vast expanse of an ever-expanding cosmos, only to reach our telescopes now, in this fleeting moment of human history. It's a humbling reminder of how small and transient we are in the grand scheme of things, and yet, it also highlights the power of human ingenuity to decipher the cosmos. And what of the future? As telescopes grow more advanced, what else might they uncover in this cluster and others like it? Could there be even more complex lensing effects, perhaps revealing entire galaxies hidden behind the glare of brighter objects? Could there be gravitational echoes of unseen objects, rogue planets, wandering stars, or even isolated black holes, imprinted on the light that reaches us? The smiling galaxy cluster serves as a cosmic treasure map, pointing us toward discoveries that may fundamentally alter our understanding of the universe. In the end, SOSS J1038+4849 is far more than just a beautiful image or a scientific curiosity. It is a challenge, a mystery, and an invitation to explore the limits of human knowledge. As we stare into the cosmic smile, we are reminded of the infinite possibilities that lie beyond, waiting for us to uncover them. And perhaps, just perhaps, the greatest discoveries of all are those we have yet to even imagine. The mysteries of the smiling galaxy cluster deepen when one considers the potential for this gravitational lens to reveal truths not only about the distant past but also about the fate of the universe itself. The light that has been bent and distorted into arcs and rings offers clues not only about the galaxies behind it but also about the invisible forces shaping the cosmos. Could SOSS J1038+4849 hold the key to understanding the ultimate destiny of the universe? One of the most profound questions in modern cosmology concerns the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. The smiling cluster provides a unique laboratory for studying this enigmatic phenomenon. By analyzing how the cluster distorts light from distant galaxies at varying redshifts, scientists can measure the universe's expansion rate over time. These measurements could help refine the elusive Hubble constant, the value that quantifies this expansion. But what if the results defy current theories? What if SOSS J1038+4849 reveals evidence that the expansion of the universe is not constant but fluctuates in ways we cannot yet explain? Even more intriguingly, some researchers speculate that gravitational lenses like this one could uncover evidence of phantom energy, a hypothetical form of dark energy that grows stronger over time, potentially leading to a big rip. In this scenario, the accelerating expansion of the universe would eventually tear apart galaxies, stars, and even atoms themselves. Could the light passing through the smiling galaxy cluster be whispering hints about this apocalyptic future? Beyond dark energy, the cluster's gravitational lensing also provides a window into the earliest epochs of cosmic history. The light from the magnified galaxies behind SOSS J1038+4849 may carry the faint signatures of the reionization era, a period when the first stars and galaxies began to ionize the hydrogen that filled the universe after the Big Bang. Studying this light in detail could reveal when and how this critical transition occurred, offering a glimpse into the dawn of structure formation in the cosmos. But what if it also reveals something unexpected, anomalous patterns in the distribution of matter or light that challenge our current understanding of the early universe? One of the most tantalizing possibilities is that the smiling cluster could help confirm, or refute, the existence of hypothetical particles like axions. These particles, if they exist, might constitute a significant portion of dark matter and could subtly alter the way light behaves as it passes through the gravitational field of the cluster. Detecting such effects would not only solve one of the greatest mysteries in physics but also open a new chapter in our understanding of the fundamental forces shaping reality. The symmetry of the smile itself also raises fascinating questions about the nature of chance and alignment in the universe. Why do we see such a perfect arrangement of features in this cluster? Is it a coincidence, or could it point to a deeper underlying structure in the cosmos? Some theorists suggest that such alignments might be more common in a universe governed by principles we do not yet fully understand, principles that could hint at higher dimensions or even multiverse theories. Could the smiling galaxy cluster be a subtle clue pointing toward a broader, hidden framework of reality? As humanity prepares for the next generation of astronomical tools, including projects like the European Extremely Large Telescope, ELT, and advanced space-based observatories, the potential for discovery surrounding SOSS J1038+4849 only grows. These instruments will allow us to study the cluster in unprecedented detail, detecting faint distortions and faint galaxies that current telescopes cannot resolve. They might even reveal gravitational lensing effects caused by smaller scale structures, such as rogue black holes or dense clumps of dark matter. In the distant future, as humans venture beyond Earth to establish observatories on the Moon or Mars, the smiling cluster could become a cornerstone for interplanetary science. Observations from different vantage points in the solar system could provide new insights into how light bends around massive objects, offering a unique test of Einstein's theory of general relativity on cosmic scales. But perhaps the most profound mystery of all lies in the cluster's ability to inspire. Why does the sight of a smile in the cosmos resonate so deeply with us? Is it because it reminds us of our own humanity, our quest for meaning in the vastness of space? Or is it because, on some level, it feels like the universe itself is acknowledging our curiosity, inviting us to look closer, dig deeper, and dream bigger? The smiling galaxy cluster is more than just a gravitational lens, it is a message. A message that the universe, vast and mysterious as it is, still has wonders to reveal. And as we continue to peer into its smiling face, we are reminded that every discovery brings us closer to understanding not just the cosmos, but our own place within it. As we continue to explore the mysteries of the smiling galaxy cluster, one cannot help but imagine the countless untold stories hidden within its arcs of light. Every curve, every distortion is a silent testament to the cosmic forces at play over billions of years. Yet, while we marvel at the patterns we can see, we must also consider the invisible, the unseen players shaping this galactic masterpiece. Among these invisible forces, dark matter looms largest. We know it is there, not from direct observation, but from its undeniable effects on gravitational lensing. In SOSS J1038+4849, the precise arcs and shapes of the lensed galaxies reveal the distribution of this mysterious substance. But what if the cluster holds clues about something even stranger? Some theories propose that dark matter could be self-interacting, meaning that it might collide and interact with itself under specific conditions. This behavior, if detected, would upend our current understanding of the cosmos, forcing us to rethink the role of dark matter in shaping galaxies, clusters, and the universe as a whole. Beyond dark matter, there is the tantalizing possibility of uncovering evidence of even more exotic physics. Could there be new particles or forces influencing the light that bends through this cluster? Some researchers have speculated that phenomena like sterile neutrinos or ultralight axions could leave subtle, detectable imprints in gravitational lensing patterns. These discoveries would not only solve long-standing mysteries about the nature of the universe but could also point to entirely new realms of physics, pushing the boundaries of what we thought possible. Yet the mysteries of the smiling galaxy cluster do not end with the physical. There is also the philosophical, the strange symmetry of its features, the almost deliberate way it seems to form a face. Some have argued that this is merely a trick of perspective, a random alignment of cosmic elements. But others wonder, what if there is something deeper at play? What if the universe is governed by hidden patterns, an order we are only beginning to glimpse? The cosmic smile is a reminder that the universe is not just a collection of random events, it is a tapestry of connections, each thread weaving into another to create the grand design we call reality. The gravitational lensing of SOSS J1038+4849 also invites us to consider the sheer scale of the universe. The galaxies behind the cluster, magnified into arcs and rings, are not just distant, they are ancient. They formed when the universe was a fraction of its current age, during a time when the first stars and galaxies were struggling to emerge from the primordial darkness. Their light has traveled billions of years to reach us, carrying with it a story of creation, destruction, and evolution. In studying these galaxies, we are not just looking at objects, we are looking at epochs, snapshots of a universe in flux. What's even more fascinating is that this light, distorted and magnified by the cluster, allows us to see deeper into the universe than ever before. Gravitational lensing acts as a natural telescope, amplifying faint and distant objects that would otherwise remain invisible. But what if the smiling cluster reveals something entirely unexpected, perhaps galaxies that formed earlier than current theories allow, or even hints of phenomena that predate the Big Bang itself? Such discoveries would force us to reconsider the very foundations of cosmology, reshaping our understanding of the universe's origins and ultimate fate. There is also the question of what lies hidden within the cluster itself. SOSS J1038+4849 is not just a lens, it is a bustling community of galaxies, each with its own history and mysteries. Within this cosmic neighborhood, stars are being born and dying, supernovae are exploding, and black holes are consuming matter. Could the cluster harbor phenomena we have never observed before, such as intermediate mass black holes or rogue stars ejected from their galaxies? Could it even contain objects that defy classification, existing outside our current understanding of astrophysics? The more we study this cluster, the more it seems to offer a gateway to the past, a laboratory for testing the limits of physics, and a mirror reflecting our deepest questions about existence. As we build more powerful telescopes and develop more sophisticated models, the smiling galaxy cluster will undoubtedly reveal even more of its secrets. But it will also remind us of how much we have yet to learn, how much remains just out of reach. And so, we are left to wonder, what will we discover next? Will the light from this cluster reveal a new force of nature, a hidden dimension, or the first whispers of a parallel universe? Or will it simply deepen the mystery, showing us how little we truly know about the cosmos? The smiling cluster is a challenge, a cosmic puzzle that dares us to push the boundaries of science, to question everything we think we know, and to embrace the unknown. As we peer into the face of the universe, shaped by light and gravity, we are reminded of one undeniable truth: the universe is alive with wonder, waiting for us to explore its depths. And in that exploration, we may one day find answers not only to the mysteries of the cosmos but to the mysteries of ourselves. For in the smile of a galaxy cluster, we see not just the universe, but the boundless curiosity of humanity staring back. The smiling galaxy cluster, SOSS J1038+4849, is more than a snapshot of the distant cosmos, it's an evolving story, one that intertwines humanity's pursuit of knowledge with the mysteries of the universe. Every detail of this gravitational lens hints at layers of complexity that we have only begun to unravel. But what if the most extraordinary discoveries are the ones we have not yet considered? One of the most exciting prospects is the potential for SOSS J1038+4849 to challenge the standard cosmological model. Our current understanding of the universe, known as lambda cold dark matter, lambda CDM, rests on the interplay of dark energy, dark matter, and ordinary matter. While this model has successfully explained many phenomena, gravitational lenses like the cosmic smile offer a unique opportunity to test its limits. If the mass distribution inferred from the lensing effects deviates from predictions, it could signal the need for a new paradigm, one that might incorporate unknown physics or revise our understanding of the universe's structure. The cluster's role as a lens also invites speculation about what lies behind it, even farther than the magnified galaxies we can currently observe. Could it reveal the light from the universe's first moments, perhaps the elusive population 3 stars, the very first stars ever to form? These stars, composed purely of hydrogen and helium, have never been observed directly. Yet, gravitational lenses like SOSS J1038+4849 could amplify their faint light, providing a glimpse into the cosmic dawn. Such a discovery would be revolutionary, offering direct evidence of the universe's transition from darkness to light. But the cluster's lensing potential extends beyond stars and galaxies. Some scientists believe that gravitational lenses might one day help detect other phenomena, such as cosmic strings, hypothetical defects in spacetime left over from the universe's formation. If these strings exist, they could subtly warp spacetime, creating unique and distinctive lensing effects. Could the smiling cluster be harboring such hidden relics of the early universe, waiting to be detected by the next generation of telescopes? The cluster itself also presents mysteries. Its mass is distributed in a way that creates an almost uncanny symmetry in the lensing effects, forming the distinctive smile and eyes. But why is this cluster so precisely aligned? Statistically, such a perfect arrangement is incredibly rare. Could this symmetry suggest a deeper cosmic alignment or hint at an unseen organizing principle in the universe? Some theorists have proposed that large-scale structures in the cosmos, such as filaments of the cosmic web, may influence the formation and alignment of galaxy clusters. If true, SOSS J1038+4849 might serve as a critical piece of evidence for understanding these vast and intricate networks. The possibility of discovering entirely new forms of matter or energy within the cluster is another tantalizing avenue. Dark matter, while the leading explanation for the unseen mass in the universe, is not the only candidate. Alternative theories suggest that clusters like this one might reveal traces of dark fluid, a hypothetical substance that combines the properties of dark matter and dark energy. If such a substance exists, its effects on the cluster's gravitational field might leave detectable signatures in the lensing patterns. The light from SOSS J1038+4849 also challenges us to think about the scale of time. The galaxies behind the cluster are seen as they were billions of years ago, but the cluster itself is also a relic of the past. It formed over countless eons, as smaller groups of galaxies merged under the influence of gravity. Observing its current state is like reading the final chapters of a book whose opening pages we can only guess at. Yet, by studying similar clusters at different distances, and therefore at different times in cosmic history, we can begin to piece together the story of how such colossal structures came to be. And what of the future? The smiling galaxy cluster is a snapshot of a moment in time, but it is not static. Over billions of years, the galaxies within it will continue to interact, collide, and merge, reshaping the cluster's structure. These processes are governed by the invisible hand of gravity, a force that not only binds galaxies together but also drives their eventual fates. Could long-term observations of SOSS J1038+4849 reveal patterns in how galaxy clusters evolve, offering a glimpse into the distant future of the cosmos? There is also the question of what lies beyond the cluster, regions of space so distant that their light has not yet reached us. As the universe continues to expand, some of these regions may never become visible, their light forever beyond our reach. This raises profound philosophical questions. Is the smiling cluster a reminder of the limits of human observation, or is it an encouragement to keep pushing those limits, to build instruments capable of seeing farther and deeper than ever before? Perhaps the greatest mystery of all is the one we have not yet conceived. The smiling galaxy cluster is a beacon of discovery, but it is also a reminder of how much remains unknown. Its arcs and rings are not just images, they are questions, challenges, and invitations. They remind us that the universe is not just a place to be observed but a puzzle to be solved, a story to be understood. And as we stand on the threshold of new technologies and new discoveries, the smiling cluster continues to inspire. It whispers to us of infinite possibilities, of secrets waiting to be uncovered. It dares us to look deeper, to dream bigger, and to embrace the unknown. For in the vast expanse of the cosmos, where light bends and galaxies dance, we find not only the mysteries of the universe but also the boundless curiosity of humanity reflected back at us, like a cosmic smile. The smiling galaxy cluster, SOSS J1038+4849, continues to be more than just a scientific marvel. It is an enigma that challenges our understanding of the cosmos, pushing the boundaries of what we know and daring us to confront the unknown. Every curve of its gravitational lens, every arc of distorted light, is a clue left by the universe, teasing us with the promise of answers to questions we haven't even thought to ask. One of the most provocative questions is whether the smiling cluster could reveal phenomena beyond our current comprehension of physics. The precise alignment of its arcs and the stunning symmetry of its features hint at an underlying order that seems too perfect to be purely coincidental. Could this cluster be a natural artifact of cosmic evolution, or might it suggest the existence of universal principles that govern not just matter and energy, but patterns on a grand, almost artistic scale? Some theorists have even speculated about the possibility of cosmic resonances, hidden harmonies in the universe that influence how galaxies and clusters form and align. If such resonances exist, SOSS J1038+4849 could be the first observational evidence of their reality. Beyond the cluster itself, the distant galaxies magnified by its gravitational lens hold their own secrets. Among them may lie the earliest galaxies to form after the Big Bang, their faint light amplified just enough to reach us. What if, hidden within this amplified light, we find galaxies that defy current theories of formation, galaxies that are too massive, too complex, or too chemically enriched for their age? Such a discovery would force a complete rethinking of how the first stars and galaxies came into existence, rewriting the story of the early universe. And then there are the invisible players in this cosmic drama. The dark matter that shapes the lensing effects of the cluster remains one of the greatest mysteries in physics. While its gravitational influence is undeniable, its true nature is elusive. Could the smiling cluster harbor evidence of exotic forms of dark matter, such as ultralight particles or dark photons? These hypothetical particles could subtly alter the cluster's gravitational field, leaving faint but detectable anomalies in the lensing patterns. Such a discovery would not only confirm the existence of dark matter but also reveal its fundamental properties, bringing us one step closer to solving a mystery that has puzzled scientists for decades. Even more tantalizing is the possibility of finding evidence of higher dimensions. According to some theories, the universe we observe is just a surface within a higher dimensional space. These extra dimensions, though hidden from our direct view, could influence the behavior of gravity on cosmic scales. The light bending around SOSS J1038+4849 might carry faint signatures of these dimensions, detectable as subtle deviations from predictions made by Einstein's theory of general relativity. If such signatures were found, they would revolutionize our understanding of reality itself, revealing a universe far more complex than we ever imagined. But the mysteries of the smiling galaxy cluster are not confined to the distant past or the hidden dimensions of spacetime. They also raise profound questions about the future. As we peer deeper into the cosmos, we are inevitably confronted with the ultimate fate of the universe. Will it continue expanding forever, its galaxies drifting apart until the night sky is empty? Or will some unknown force bring this expansion to a halt, triggering a cosmic collapse? The smiling cluster, with its gravitational lensing effects, provides a unique tool for studying dark energy, the mysterious force driving the universe's accelerated expansion. By analyzing the lensing patterns at different redshifts, scientists can track how dark energy behaves over time, and perhaps uncover hints of its ultimate destiny. The cluster's gravitational lensing also offers an opportunity to study the most extreme and rare events in the universe. Among the magnified galaxies, there may be supernovae, gamma-ray bursts, or even the light from merging black holes, events so distant and faint that they would otherwise be invisible. Could SOSS J1038+4849 act as a cosmic magnifying glass, revealing these fleeting phenomena and giving us a closer look at the violent processes that shape the universe? And yet, even as we unravel its secrets, the smiling cluster remains a mystery in itself. Why does it appear to smile at us, its features so strikingly familiar? Is this symmetry purely coincidental, or does it hint at something deeper, perhaps a universal tendency for matter and energy to arrange themselves in patterns that resonate with the human mind? Some philosophers and cosmologists have speculated that such phenomena might reflect a fundamental connection between consciousness and the cosmos, a tantalizing idea that challenges the very foundations of science. As we look into the smiling cluster, it feels as though the universe is looking back, inviting us to explore, to question, to wonder. What lies beyond the visible? What truths remain hidden in the fabric of spacetime, waiting to be revealed? The cluster is a reminder that the cosmos is not just a collection of stars and galaxies, it is a living, breathing enigma, full of stories yet to be told. And so, the smiling galaxy cluster becomes a symbol, not just of what we know, but of all that we have yet to discover. It dares us to imagine the unimaginable, to dream of a universe that is richer, stranger, and more beautiful than anything we have ever conceived. And as we continue to study its light, we are reminded of one simple, profound truth: the universe is vast, mysterious, and endlessly full of wonder. The smiling galaxy cluster remains a cosmic enigma that transcends its whimsical nickname, offering a portal into some of the most profound and unresolved questions in astrophysics. As we continue to analyze the intricate details of SOSS J1038+4849, it becomes increasingly clear that this gravitational lens is more than just a scientific curiosity, it is a Rosetta Stone for understanding the mechanics, history, and future of the universe. The gravitational lensing patterns created by SOSS J1038+4849 provide an unparalleled opportunity to map the elusive distribution of dark matter. Unlike the luminous galaxies that we can observe directly, dark matter reveals itself only through its gravitational influence. The precise arcs and rings around the cluster are a direct manifestation of dark matter's unseen mass, bending light from distant galaxies into strikingly coherent forms. However, The study of this cluster has revealed peculiarities in the dark matter distribution. Some areas exhibit gravitational effects that don't align perfectly with visible matter, suggesting that dark matter may clump in unexpected ways. Could this cluster harbor evidence for alternative theories, such as warm dark matter, composed of lighter, fast-moving particles, or self-interacting dark matter, where particles weakly collide with one another? Observations of the smiling cluster have already prompted the development of new computational models to explore these possibilities, pushing the boundaries of theoretical physics. Furthermore, some scientists propose that dark matter might be linked to entirely new forces of nature, ones that don't interact with ordinary matter in ways we currently understand. If so, clusters like SOSS J1038+4849 might act as experimental testbeds, helping to identify anomalies that hint at the existence of such forces. The extraordinary lensing effects of the smiling cluster offer more than a view of distant galaxies, they also magnify transient cosmic phenomena. Among the most exciting possibilities is the detection of gravitational waves passing through or near the cluster. Gravitational waves, ripples in spacetime caused by massive cosmic events like black hole mergers, might interact subtly with the curved spacetime of the cluster. This interaction could leave faint, measurable signatures in the lensing patterns, potentially revealing details about the wave's origins and properties. Observing such effects would open a new window into multi-messenger astronomy, where light, particles, and gravitational waves are studied together to create a more complete picture of cosmic events. Another tantalizing possibility is that the smiling galaxy cluster could contain evidence of primordial black holes, hypothetical remnants of the Big Bang that may have formed from density fluctuations in the early universe. These black holes, much smaller than their stellar or supermassive counterparts, could account for at least some fraction of dark matter. If primordial black holes exist, they might create subtle distortions in the gravitational lensing patterns observed around SOSS J1038+4849. Identifying these distortions would not only confirm the existence of these exotic objects but also provide insights into the universe's earliest moments, offering a glimpse into conditions that existed mere fractions of a second after the Big Bang. The smiling cluster is not an isolated structure, it exists as part of the larger cosmic web, a vast network of filaments composed of dark matter, gas, and galaxies that spans the universe. This web serves as the framework upon which galaxy clusters form and grow, and SOSS J1038+4849 provides a rare opportunity to study this structure in detail. By analyzing how light from background galaxies is distorted as it travels through the cluster, scientists can reconstruct the three-dimensional distribution of matter in the surrounding cosmic web. This information could help answer key questions about how dark matter flows through the universe, how galaxy clusters accumulate mass over billions of years, and whether the web itself has evolved in unexpected ways. The light magnified by SOSS J1038+4849 comes from some of the most distant galaxies ever observed. These galaxies, visible only because of the lensing effect, likely formed during the universe's cosmic dawn, a period when the first stars and galaxies ignited and began to reionize the intergalactic medium. By studying these magnified galaxies, astronomers can probe the physical conditions of this critical era. Recent spectroscopic observations of galaxies behind the smiling cluster have already hinted at unusually high rates of star formation and unexpected chemical compositions. These findings challenge current models of how galaxies evolved during the universe's infancy. Could these distant galaxies contain the chemical fingerprints of population 3 stars, the first stars to form, composed entirely of primordial hydrogen and helium? If so, their detection would provide a direct window into the universe's earliest stellar generations, revealing how the first heavy elements were forged. The smiling cluster is also a key player in the study of dark energy, the mysterious force driving the accelerated expansion of the universe. By analyzing how the cluster lenses light from background galaxies at different distances, astronomers can measure how the universe's expansion rate has changed over time. This data is crucial for refining the Hubble constant and addressing the growing tension between measurements of the universe's expansion from different methods. But what if SOSS J1038+4849 reveals something entirely unexpected, evidence that dark energy itself is not constant but evolves over time? Some theories suggest that dark energy could transition between different states, or even decay into new forms of energy. If true, this would dramatically alter our understanding of the universe's future, potentially leading to scenarios like the Big Rip, where the universe's accelerated expansion eventually tears apart galaxies, stars, and even atoms. Perhaps the most intriguing aspect of the smiling cluster is its uncanny appearance. The symmetry of its eyes and smile is a statistical anomaly, one that invites philosophical as well as scientific reflection. Is this formation merely a random alignment, or could it point to something more profound, a hidden order in the universe? Some researchers have proposed that such alignments might arise from deeper patterns in the fabric of spacetime itself. These patterns, if real, could be remnants of quantum fluctuations from the very birth of the universe, frozen into the cosmic web over billions of years. If SOSS J1038+4849 represents such a pattern, it might provide a new way of understanding the fundamental structure of reality. As new observatories like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, begin their operations, the smiling cluster will undoubtedly become a focal point of study. These instruments will allow astronomers to resolve finer details in the lensing patterns, detect even fainter background galaxies, and search for subtle anomalies that hint at new physics. Ultimately, the smiling galaxy cluster serves as a symbol of the boundless potential for discovery. It is a reminder that the universe, in all its vastness and complexity, still has secrets to reveal, secrets that challenge us to think bigger, dig deeper, and embrace the wonder of the unknown. As we continue to explore its mysteries, SOSS J1038+4849 will remain a beacon of curiosity, an invitation to dream of what lies beyond, and a testament to the power of human ingenuity in unraveling the cosmos. The smiling galaxy cluster continues to stretch the limits of human curiosity in scientific exploration, standing as a reminder that each cosmic puzzle solved inevitably leads to new questions. With every photon of light that passes through the gravitational lens of SOSS J1038+4849, the universe seems to whisper tantalizing secrets about its history, its structure, and perhaps even its ultimate destiny. The cluster's smile may appear lighthearted, but its scientific implications delve into some of the heaviest and most profound topics in cosmology. The light passing through the smiling cluster is not just a visual phenomenon, it's a carrier of information about the distant past. Through spectroscopic analysis of the galaxies magnified by the lens, astronomers are uncovering key insights into the chemical composition, temperature, and movement of stars that formed billions of years ago. Some of the light reveals galaxies so faint and distant that their spectra have been stretched to extreme redshifts, an effect caused by the universe's expansion. Interestingly, the highest redshifts observed behind SOSS J1038+4849 push into a period when the universe was less than 1 billion years old. This era, known as the Epoch of Reionization, represents the cosmic awakening, when the first galaxies and quasars ionized the surrounding hydrogen gas and began transforming the dark, neutral universe into the luminous cosmos we see today. By studying these magnified galaxies, scientists are piecing together a timeline of how the universe transitioned from primordial simplicity to the complex web of stars, galaxies, and clusters that populate it now. What makes the smiling cluster even more compelling is its ability to amplify the light of extremely faint galaxies. Some of these galaxies appear to be in the process of merging, an event that triggers intense star formation and may seed the growth of supermassive black holes. Could these magnified galaxies offer a direct view of how the first black holes formed and evolved? If so, they could help resolve one of the most perplexing mysteries in astrophysics: how supermassive black holes managed to grow so quickly in the early universe. Beyond the mysteries of star formation and black holes, SOSS J1038+4849 serves as a natural tool for probing the nature of dark energy. This mysterious force, which accounts for roughly 70% of the universe's energy content, is responsible for its accelerated expansion. But why is the expansion speeding up, and why now? These are questions that continue to baffle cosmologists. Gravitational lenses like the smiling cluster provide a powerful way to measure the rate of expansion at different points in cosmic history. By analyzing how light is bent and magnified at various redshifts, scientists can track how the influence of dark energy has changed over billions of years. Current data from SOSS J1038+4849 supports the standard cosmological model, in which dark energy appears to act like a cosmological constant. However, subtle deviations in the lensing patterns could suggest otherwise. Perhaps dark energy's effects evolve with time, or perhaps it interacts with dark matter in ways that remain hidden from view. If such evidence were found, it could hint at new, exotic physics, a dynamic dark energy field, or quintessence, that changes over time. Alternatively, it could point to modifications of Einstein's general relativity, revealing that our understanding of gravity itself might be incomplete. Clusters like SOSS J1038+4849 are at the frontier of these investigations, acting as cosmic laboratories where the deepest questions about the universe are being tested. The cluster's role within the larger cosmic web is another source of fascination. The web, an intricate network of filaments connecting galaxies and clusters across the universe, represents the scaffolding upon which cosmic structures form. SOSS J1038+4849, as part of this web, offers a unique opportunity to study how galaxy clusters interact with their surroundings. Recent simulations suggest that gravitational lenses like the smiling cluster might reveal evidence of streaming flows of dark matter within the web. These flows, predicted by advanced cosmological models, could show how matter flows into clusters along filaments, feeding their growth over billions of years. If detected, these flows would provide direct observational evidence of the cosmic web's dynamic nature, offering insights into how clusters evolve and how galaxies within them are shaped by their environment. What's even more exciting is the possibility that SOSS J1038+4849 might reveal hidden dimensions of the universe itself. Some theories of quantum gravity and string theory suggest that additional spatial dimensions could influence the behavior of gravity on large scales. If true, these hidden dimensions might leave subtle imprints on the lensing effects of massive objects like galaxy clusters. By studying the lensing patterns of SOSS J1038+4849 with extreme precision, scientists might uncover clues about the true nature of spacetime, an outcome that would revolutionize our understanding of the universe at its most fundamental level. The smiling cluster also serves as a reminder that the universe is not static, it is dynamic, constantly evolving. Over the next billions of years, the galaxies within SOSS J1038+4849 will continue to interact, collide, and merge, creating new structures and transforming the cluster's appearance. Observing it now is like capturing a single frame of an epic cosmic movie, one that spans incomprehensible timescales. By studying clusters at different distances, astronomers can essentially rewind and fast-forward the movie of cosmic history, observing how structures like SOSS J1038+4849 form and evolve. This comparative approach has already revealed surprising trends, such as the tendency for clusters to contain more red and dead galaxies, those that have stopped forming stars, as they age. However, the detailed processes driving these changes remain unclear. Could the smiling cluster help unravel the mechanisms behind galaxy quenching, shedding light on why some galaxies thrive while others fade away? Ultimately, the smiling galaxy cluster is a symbol of the profound interconnectedness of all things. Its light, bent and shaped by gravity, has traveled billions of years to reach us, carrying with it the story of distant galaxies, unseen forces, and the earliest moments of creation. But it also reminds us that science is as much about asking questions as it is about finding answers. Each new discovery raises more mysteries, drawing us deeper into the beauty and complexity of the cosmos. The cluster's smile, while seemingly playful, is a challenge. It dares us to continue exploring, to push the boundaries of human knowledge, and to confront the unknown with curiosity and wonder. As telescopes become more powerful and our understanding of the universe grows, SOSS J1038+4849 will remain a touchstone for discovery, a cosmic reminder that the greatest mysteries are often hidden in plain sight, waiting for us to look just a little closer. The story of the smiling galaxy cluster, SOSS J1038+4849, does not have a definitive conclusion. It is, in many ways, an ongoing chapter in humanity's exploration of the universe. Its arcs and rings of light stretch across spacetime, inviting deeper investigation, greater technological innovation, and a profound philosophical reflection on our place in the cosmos. What we see today is not just a beautiful anomaly or a scientific tool, but a cosmic artifact that links the distant past with the boundless future, an emblem of discovery that compels us to look outward and onward. The smiling cluster embodies a unique intersection of wonder and rigorous science. Its whimsical appearance, reminiscent of a face smiling back at us, is a poignant reminder of the human capacity to see patterns, to find meaning even in the vast randomness of the cosmos. And yet, beneath that light-hearted appearance lies a complex tapestry of astrophysics, an intricate dance of light, gravity, and spacetime that scientists are working tirelessly to decode. In every detail of this cluster, there are stories of ancient galaxies forming in the chaotic early universe, of dark matter sculpting the cosmos in silence, of light traveling billions of years, weaving through the fabric of spacetime to reach our telescopes. These are stories that connect us, across unimaginable scales of time and space, to the universe's very origins. The smiling galaxy cluster is not merely an object of study, it is a promise of discoveries yet to come. As technology evolves, so too will our ability to unlock its secrets. The next generation of telescopes, such as the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and future space-based observatories, will allow us to peer deeper into the cluster's lensing effects, uncovering fainter, more distant galaxies than ever before. These instruments may even detect the chemical signatures of the first stars, revealing how the cosmos lit up for the first time. Gravitational lensing studies will become more precise, thanks to advanced modeling techniques and artificial intelligence algorithms capable of analyzing vast datasets. These tools will help us map the distribution of dark matter with unprecedented accuracy, identify potential anomalies in gravitational physics, and refine our understanding of the universe's expansion rate. Perhaps SOSS J1038+4849 will even play a pivotal role in solving the Hubble tension, the ongoing discrepancy in measurements of the Hubble constant, bringing us closer to answering one of cosmology's greatest mysteries. But even as we uncover new details about the smiling cluster, it remains a portal to the unknown. Its arcs and distortions may hold clues to phenomena we cannot yet imagine, hidden dimensions, exotic particles, or the interplay of forces beyond the standard model of physics. Could this cluster's lensing patterns be subtly influenced by the effects of quantum gravity, or by remnants of the universe's earliest moments? What if its symmetry is not merely a coincidence but a sign of an underlying order that transcends our current understanding? These questions drive home an important truth: the universe is a vast, dynamic, and mysterious place, far richer and stranger than our limited senses and tools can currently grasp. Every observation of SOSS J1038+4849 is a step closer to comprehending not just the cluster itself but the fundamental nature of reality. And yet, with every answer, new questions will arise, ensuring that the journey of discovery is never-ending. Perhaps what makes the smiling galaxy cluster so profoundly meaningful is the way it connects us to the cosmos. Its light has traveled billions of years to reach us, a journey that began long before humanity existed and will continue long after we are gone. Yet, in this fleeting moment of cosmic time, we have the privilege of witnessing it, of interpreting it, of finding meaning in its arcs of light. The cluster reminds us of our capacity for curiosity and exploration, of our drive to understand the universe even when it seems incomprehensibly vast and complex. It is a testament to the power of human ingenuity, a symbol of how far we have come in our quest to decipher the cosmos, and how much farther we still have to go. Ultimately, the smiling galaxy cluster is not just a scientific puzzle or a celestial wonder, it is an invitation. An invitation to keep asking questions, to look deeper, to push the boundaries of what we know and what we think is possible. It invites us to embrace the unknown, to find joy in the search for answers, and to recognize that the universe is as much a mystery as it is a mirror of our own infinite curiosity. Its smile is a reminder that discovery is not just about the answers we find, it's about the journey, the moments of awe and wonder that come from looking up at the night sky and realizing how small we are, yet how connected we are to everything around us. The smiling galaxy cluster is a cosmic gift, a beacon of light and mystery that will continue to inspire scientists, dreamers, and explorers for generations to come. As we peer into its distant arcs of light, we are not just studying the universe, we are participating in a grand, ongoing story, a story that began with the birth of the cosmos and continues through us, as we search for meaning in the vast and beautiful unknown. And perhaps, as we uncover more about this smiling cluster, we will find that the greatest discoveries lie not only in the universe's distant past but in the boundless future it promises.